For this lesson, we're continuing our look at patterns and sequences. And in this case, we're going to be taking a look at a sequence that it occurs commonly enough that it gets its own special name. It's called a geometric sequence, and it gets its own special formula or representation that we want to become comfortable with so that we can get to using it right away. So as I did in a previous lesson on arithmetic sequences, I'm going to start off with taking a look at some patterns. So 2, 4, 8, 16. I'm asked for the next three terms in each sequence. Hopefully you can see that the next term is going to be 32, and then after that would be 64, and then after that would be 128. If we took a look at first differences here, we would be disappointed because the values we would get, if I took a look at first differences, which I'll do over here in kind of my rough 2, 4, 8, 16, 32, etc. 4 minus 2 is 2, 8 minus 4 is 4, 16 minus 8 is 8, 32 minus 16 is 16. You can see all it's done is shifted down and I have the exact same set of numbers. And if I did that again with second differences, it's again the same set of numbers shifted down. So first, second, third differences are not going to do us any good here. But we have to think about, well, how did we change? How did we recognize this pattern? And it's actually recognizing that the change between these is actually multiplication. It's not addition or subtraction, which is what your first differences tell you. In this case, what we're actually interested in are ratios. So 2 times 2 gives me 4, times 2 gives me 8, times 2 gives me 16. Or another way to think of it is in terms of ratios. So if I did this, typically if this was our y value, if I then did the ratio y2 divided by y1, what's 4 divided by 2? 2. What's 8 divided by 4? 2. 16 divided by 8 is 2. 32 divided by 16 is 2. And when you have ratios like this, so this has a what's known as a common ratio, and that common ratio is 2. That's actually an exponential function. So this is something we've looked at before, but now we're going to look at it in a slightly different way. And so I wanted to give you that background, but let's press forward now and see if we can continue to make some sense of this. So the idea that we're multiplying each time, so let's look at it from the other direction. What did I multiply 1 by to get negative 2? And the answer was I multiplied by negative 2. And then negative 2 times negative 2, that gives me positive 4. Times negative 2 gives me negative 8. Times negative 2 gives me positive 16. Then negative 32. And then positive 64. Now, how about this next one? 27. What do I multiply 27 by? You might think of that as, well, I don't think of that as multiplying. I think of that as dividing by 3. And you wouldn't be wrong, because that is what we're doing here. Divide by 3 and divide by 3. But it really is, in keeping with the way we're going to represent this, it's actually more useful to think of this as a multiplication, which of course is a pretty simple thing to do. To divide by 3 is the same as multiplying by a third. So long as you are comfortable with that kind of basic algebra skill, then, well, what is 1 multiplied by a third? That now tells us our next term is just 1/3. And then 1/3 multiplied by a third is 1/9. And then 1/9 multiplied by a third is 1/27. So these are geometric sequences, which are related to exponential functions. So let's take a look with that in mind. We've got this sequence, 5, 10, 20, 40. So let's find the eighth term, and let's just do it manually. So what's the next term? Well, hopefully you can see that each time what's happening here is I'm doubling. So the next term will be 80, 160, 320, and 640. Okay, write an expression for the nth term, a general expression. Now, I want you to recall for arithmetic, so for an arithmetic sequence, we already went through this exercise. The generic term for an arithmetic sequence is a plus n minus 1 times d. This is my start value. This is my step size, which is known as the common difference. And this is essentially my number of steps. We actually want to come up with something very similar for our geometric sequence. The difference is going to be, well, we have a starting value, a starting value of, in this case, 5. How did I change 5 into 10? You know what I'm going to do? We did the same thing with the arithmetic. So let's go ahead and do it the same way. T1 is equal to 5. T2 is equal to 10. How did I change 5 into 10? I multiplied by 2. So that means I could actually write T2 a different way. I could write T2 as 5 multiplied by 2. Okay, T1 is equal to 5 and T3 is equal to 20. How did I change from 5 into 20? I had to multiply by 2 to turn it into 10, and I had to multiply it by 2 again to turn it into 20. So essentially I multiplied by 2 squared. So I could rewrite this as starting at 5 multiplied by 2 multiplied by 2, which of course is the same thing as starting at 5 multiplied by 2 squared. One last time, T1 equals 5. What is T4? T4 was equal to 40. What is my generic way of writing this? This is 5. Well, 5 times 2 is 10, times another 2 is 20, times another 2 is 40. So this is actually the same as 5 times 2 cubed. So can we write Tn? Well, Tn starts off with 5, multiplies it by 2. How many times does it multiply it by 2? For T2, we multiplied it once. For T3, we multiplied it twice. For T4, we multiplied it 3 times. For Tn, we would multiply it by n minus 1 times. Whatever this number is, it has to be 1 less than that. And there is our generic. Sorry, that's not A, that's B. We already answered A because A was up here. So there's the answer to A. There's the 8th term. So now we have our general expression, 5 times 2 to the n minus 1. This is where that tie-in to exponential functions comes from. And now we've been asked, the last part of the question, where would you find 5,120 in this sequence? Now, first of all, it tells us in this sequence. So it's understood that this is an actual number in the sequence. If we just wrote out the sequence, eventually we would end up here at 5120. But that's not very elegant. And it's really, if I ever ask you a question like that, it's not what I'm looking for. So I want to know if Tn is 5120, what is the value of n that goes along with that? So what I do is I put that into my general expression. So I replaced Tn with 5120, and now I'm going to solve for n. And because it is in the sequence, this should work out nicely. I should get an integer value for n. Now the first thing I need to do is get rid of that 5 in front. That 5 in front is multiplication, but the rest of this thing is an exponential function. So I need to respect my order of operations, get rid of that 5 first. 5120 divided by 5 is 1024. 2 to the n minus 1. Now, if you've done your unit on exponential functions, then hopefully you have an idea of what you're supposed to do here. And the answer to that is you're supposed to come up with a common base. So how can I write 1024 as 2 to the power something? Now, that may be as much work as just writing out this entire sequence. But especially things like powers of 2, they're pretty common. And so if you work this out, if we just start 2, 4, 8, 16, 32, you don't have to write this out. I'm just doing this once. 64, 128, 256, 512, 1024. It is a power of 2. And this would be 2 to the 1 to the 2, 3, 4, 5, 6, 7, 8, 9, 10. And for those of you who are more computer literate, particularly in dealing with binary numbers, you might recognize this. So 2 to the 10 is equal to 2 to the n minus 1, which of course implies that the exponents themselves must be equal to each other. And I end up with a value of n is equal to 11. So therefore, 5120 is term number 11. Okay. So what does that look like in general? This is a very similar treatment to what we did with arithmetic sequences. The difference is instead of adding multiple steps, we're multiplying by multiple steps. Instead of calling those steps a common difference, now they are referred to as a common ratio. We still have our first term, which we call a. That could be also called T1, or it could be called f of 1. So the first term, T1, is there. T2, which would help if I could actually write that correctly. T2 requires one multiplication of the common ratio. T3 requires two multiplications of the common ratio. So notice it's one less. T4 requires 3, and so on. So Tn requires n minus 1 multiplications. All right, how about this? Is each of these sequences geometric? If it is, what's the common ratio? Okay, well, why don't we see what the common ratio is? So if this is T1, T2, T3, T4, then the common ratio is always the second minus the first. The second, not minus, the second divided by the first. So T2 divided by T1 equals -8 divided by 2, which is equal to -4. That's the same thing as saying I take 2 multiplied by -4 gives me -8. And we can see that's true. T3 over T2 is equal to 32 divided by -8, which is also -4. And T4 over T3 is -128 divided by +32, -4. These are equal, so this is geometric. And the common ratio is -4. Okay, let's do the next one. So once again, T1, T2, T3, T4. What is T2 divided by T1? That's 2x divided by x. 2x divided by x is equal to 2. T3 divided by T2, that would be 3x over 2x. But 3x divided by 2x is the number 3 over 2. Those are not equal to each other. And so since these two things are not equal to each other, 2 is obviously not equal to 3 over 2. So therefore it is not geometric. And of course, we can't write the common ratio. Okay, how about this one? T1, T2, T3, T4. So what is T2 over T1? That's x to the 14 divided by x to the 7, which is equal to x to the 7. T3 divided by T2 is x to the 28 over x to the 14, which is x to the 14. This is not geometric because the common ratios or the ratios, they're obviously not common ratios. The ratios are different. And then giving myself a little bit more room, T2 over T1 is 4x to the 10 over 2x to the 7. 4 divided by 2 is 2. X to the 10 divided by x to the 7 is x to the 3. T3 over T2 equals 8x to the 13 over 4x to the 10. 8 over 4 is 2. X to the 13 over x to the 10 is x to the 3. What about T4 over T3? That's 16x to the 16 over 8x to the 13. 16 over 8 is 2. X to the 16 over x to the 13 is x to the 3. In this case, it is geometric, and the common ratio is actually this kind of odd looking common ratio, but 2x cubed. That's what I multiply each time. Each time going from term to term, I am multiplying by 2x cubed. So the next term would be 16x to the 16 times 2 is 32x to the 19, for example. Okay, I believe this is the last one. I've saved the most complicated for last. I think I'm going to do something here that I think will catch some students off guard or will be surprising. Can you really do that? Yes, you can really do that. We're told that this is geometric, which means it's going to follow AR to the n minus 1 is going to be the general term. So T5, which is 1875 must be equal to AR, but that's for T5, so that's going to be AR to the 4. I'm going to call that equation number 1. 46875 is going to be equal to AR to the, well, this is T6, so that would mean 6 minus 1 would be 5. I did this wrong, didn't I? Oh no, it's T7, my mistake. It's 7 minus 1, which is going to give me 6. And I'm going to call that equation 2. You have a couple of options here. One of them is you can try to do substitution. We have two equations with two unknowns. A and R are the unknowns. So two equations, two unknowns. One option I could do is I could modify equation number 1 and rewrite it as a equals 1875 over r to the 4. And then I would sub this, I could sub a into equation 2, and I end up then with 46875 equals, instead of this a value, you know what, let me do this in a different color. 46875 equals, but instead of this a, I'm actually going to substitute 1875 over r to the 4 times r to the 6. And then what I end up with here is I've got r to the 6 over r to the 4. That just gives me r squared. 1875 r squared, 46875. Now I'm going to pause here. I could continue from here, but I want to show you the other way that I think to do this, which is, this is substitution. The other way that we've learned to solve systems of equations would be by elimination, but you can't add or subtract to do that here. So what I can do is I'm going to rewrite equation number 1 here. And then what I'm actually going to do is I'm going to do equation 2 divided by equation number 1. It's going to give me the same result that I had over here, or that I'll get to over here. The first thing is 46875 divided by 1875. And I remember this just from seeing this question done recently. That's just 25. A divided by A is equal to 1. R to the 6 divided by r to the 4th gives me r squared. If I had taken this one the next step, divide by 1875, divide by 1875, I would have ended up in the same place. 25 equals r squared. So at this point, the two solutions converge, they come back together. If r squared equals 25, r is equal to, a lot of you might say, well, the answer is r is equal to 5. It's actually plus or minus 5. Both of those are valid common ratios here. And now that I know this, I actually have to split this into my two solutions. R equals 5, r equals negative 5. So what does this mean, r equals 5? Let's take a look actually at this equation number 1. Equation number 1 says 1875 equals a, but instead of r now, I'm going to write 5 to the power 4. So I get 1875 equals a, and 5 to the power 4, let's see, 5 squared, 5, that's going to be 620, is that right? 625? Yes, it is. And so from there, 1825 divided by 625 gives me a equals 3. Now, on this side, 1875 equals a negative 5 to the 4, but that's actually not going to make a difference here, because negative 5 to the power 4, that's an even exponent, I get 625. And so a equals 3. So they actually converge again. I still need to keep the two r values possible. And so therefore, let's make sure I'm answering the question that's being asked here. Yeah, it wants me to find the general term. So therefore, Tn is equal to a, which is 3, r, which is 5, to the n minus 1, or Tn is equal to 3 times negative 5 to the n minus 1. So I actually have two valid solutions for this particular problem. And the reason I asked this as my exercise was because having the plus minus made this a more difficult exercise. I could have made this somewhat simpler, having only one possible answer here, but then I didn't want students to get caught off guard if they saw that as an example or if they saw that as a homework exercise later on. And that is it for geometric sequences, at least as far as the lesson goes. Lots of practice you'll need to do to get yourself completely comfortable with this stuff.